Hello and welcome to today's tutorial. So today we will going to discuss on a few of the properties of the power spectral density, that is an addition of random process in terms of power spectral density and multiplication of random process in case of in terms of power spectral density. Let us switch back to our screen and let's say this one by one. So now as we all have seen the addition in case of the random process. Now here in case of the addition in case of random process of PSDs, how does the equation relates? So that we can write as, so W of t is equal to, it is x of t plus y of t, where x of t and y of t are the two different random process. So then in terms of its autocorrelation function, if its mean is 0, we are considered that the mean of x of t and y of t, its mean is 0, then its autocorrelation function can be written as, we already have seen in the previous tutorial, so this can be written as Rw of tau is equal to, it is Rx of tau plus Ry of tau. So this we can obtain by substituting this into, or by taking this expectation on both sides. So we know the expectation of x of t with its density function, and then we got this autocorrelation function. So same thing, if we write this in terms of the power spectral density, then this will result in, so this we can write this as Sw of omega is equal to, it is Sx of omega plus Sy of omega. So it means the addition of the random process in the time domain. So here we are trying to relate the time domain with the frequency domain. So in time domain, it is the addition of the autocorrelation of x and y, the two random process, and the same thing will result in the frequency domain. Frequency domain also results in the summation of the two random process, that is x and y. Now let us look into the multiplication. Let's set this page. So now let us look into the multiplication of random process, and we'll try to relate this with its PSD and its PSD. Then we have considered the two random process again, that is x of t and y of t, and both are independent random process. So then if you multiply these two random process, it will result in one more random process, that is W of t, which is nothing but, it is x of t into y of t. So then by taking the autocorrelation function, we will get this as a product. So Rw of tau is equal to Rx of tau into Ry of tau. Then if you apply the power spectral density for this new term or the new random process, that is W of t, then its power spectral density can be written in the mathematical form as Sw of omega is equal to, we know the definition of the power spectral density, that is minus infinity to plus infinity. That is basically written as W of, it can be written as, that is Rw in terms of tau, Rw of tau into e power minus j omega tau into d tau. Now we will substitute this with Rw of tau, so minus infinity to plus infinity, then this will be Rx of tau into Ry of tau into exponential of minus j omega tau into d tau. Now we will substitute the equation for Ry of tau in terms of the inverse spectral density. So this will become minus infinity to plus infinity, that is Rx of tau into, so we'll substitute the inverse spectral density equation, that is 1 by 2 pi into integral of minus infinity to plus infinity. Now this can be written as Sy of u into e power j omega u into du into an exponential term e power minus j omega tau into d tau. So now we will interchange the order of summation. So then we will get this as 1 by 2 pi. I'll take it outside. So 1 by 2 pi into integral of minus infinity to plus infinity. So this is Sy of tau into integral of minus infinity to plus infinity, that is Rx of tau into e power. Now there are two exponential terms. I'll take it common, so it is e power minus j of omega minus u into tau into d tau into du. Then let me save this and take the new page. So I'll continue in the next page. So then the term will result in SW of omega is equal to 1 by 2 pi. If you can see from here. So this term is nothing but your, again, looks like a spectral density equation if you look at here. So then that will be 1 by 2 pi into integral of minus infinity to plus infinity. So it is Sy of u into, now this can be written as Sx of omega minus u into du. Now this looks like a convolution integral equation. So this is finally written as 1 by 2 pi into, this is Sy of u, or we can just write this as Sx of omega convolution. So convolution is represented by star. So Sx of omega convolution with Sy of omega. So this is what we'll get when we multiply the two random processes in terms of in time domain we'll get the multiplication of the two correlation functions, but in terms of the spectral density it is the convolution of the spectral density of x and y multiplied by 1 by 2 pi. So this can be seen as a signal modulation and a demodulation if you look into an application case. So now let us look into a few examples here. Okay, so let me write here. A wide sense stationary random process has the PSD, which is defined below, that is Sx of omega, and a carrier random process, that is C of t, is defined independent, which is given below. So then we have to find its PSD and autocorrelation function. So find the PSD and actually find the autocorrelation and its power spectral density. So Sx of omega is given as, that is 5 times the cos of pi omega by 2 omega m for the range of minus omega m to plus omega m, means the value of omega range from minus omega m to plus omega m and 0 otherwise. So now we know that from the Fourier transform here. So before going to Fourier transform pair, now let me write one more definition here, that is in terms of carrier. The carrier PSD, in terms of spectrum domain, it is given as 100 pi into delta of omega minus omega naught plus delta of omega plus omega naught. So now let us find the autocorrelation definition. So autocorrelation definition for this is nothing but, so basically it's a modulation process. So modulation process is defined as multiplication of carrier signal with the modulating signal. So W of t is equal to C of t. It is C of t into X of t. So C of t is a carrier and X of t is our modulating signal. So here in case of it is a random process. So now in terms of time domain, it is represented in terms of the autocorrelation function. So now this is Rw of tau equals, this is Rc of tau into, this is Rx of tau. So now we'll find the PSD. So to find the PSD, SW of omega is equal to, it is 1 by 2 pi. So here 1 by 2 pi is nothing but, here we have the 100 pi in case of this when we multiply. So we'll get here, I'll take this term 5 into 100 pi, so that is nothing but the 500 pi by 2 pi into integral of minus infinity to plus infinity. So that is nothing but it looks like the convolution equation here. So convolution is nothing but, let us write the equation before straight away going for this. So this is nothing but 1 by 2 pi into integral of minus infinity plus infinity. It is Sx of u into Sx of omega minus u into du. So this is the actual equation. Now we are going to substitute in this case. Sx of u is, we are going to find this here. So this is nothing but in terms of its Fourier transform. Okay, so that is given here. So then when we take it common, so this will be 500 pi by 2 pi into integral of minus infinity to plus infinity. So here I will get this as in terms of delta. So this we are going to write, so delta of u minus omega naught plus delta of u plus omega naught into cos. Let me shift these terms which are not required here. So then this is cos of pi. So this should be in terms of omega minus u. So it is omega minus u by 2 omega m into du. So when we simplify this term, So finally we will get this as this is equal to 250 into, we know from the impulse property, then we can straight away apply this as equal to cos pi of omega minus omega naught by 2 omega m plus cos of pi omega plus omega naught by 2 omega m. So this is what this is SW of omega will result in these terms. So now if we plot this terms, so then we'll get something like this, and this might be the omega, and this is omega naught plus omega m, and this is omega naught minus omega m. So if we consider SW of omega is equal to 0, it means if the omega is equal to 0, then the inverse spectral density, by using that equation we can write this as RW of 0 is equal to 1 by pi into integral of 0 to infinity into SW of omega into d omega. So then when we substitute these terms back, so then we will get here as RW of 0 equals 1 by pi into integral of omega naught minus omega m. This is omega naught plus omega m into 250 of cos pi of omega minus omega naught by 2 omega m into d omega. So this is the final term we will get in terms of autocorrelation function. Now let us look into the cross spectral density here. Save this page. So let us look into the cross spectral density. So we'll consider the x of t and y of t as the two random process, and both are restricted to certain time interval. So that is both times are restricted from say minus t to plus t. Then only we can apply the Fourier transform for this case. So then its Fourier transform pair for these two random process here, that is x of t, its Fourier transform pair is x of f, and y of t, its Fourier transform pair can be written as y of f. So the cross power can be represented as its px, it can be represented as pxy. Then we know that the power equation, it is given by, it is 1 by 2t, that is the average power we are talking about. So it is minus t to plus t, then it is x of t, it is x of t into y of t into dt. So this is our power equation. So by applying the this with Parseval's theorem, so Parseval's theorem is given as p is equal to 1 by 2t into integral minus t to plus t, that is x square of t into dt equals integral of minus infinity to plus infinity. It's in terms of its frequency, it is x of f magnitude square, which is take an average with df. So this is the Parseval's theorem. So same thing we are going to apply here now. So that is given by, now this equation becomes pxy is equal to 1 by 2t into integral of minus t to plus t into x of t into y of t into dt. Now this, using Parseval's theorem in terms of the frequency domain, it is represented as minus infinity plus infinity. Now rather than taking the magnitude, so I can write this as x conjugate of f into y conjugate y of f with an average of dividing by 2t into df. So this is the equation. So now if you apply the limits to the right hand side of this equation in terms of frequency, now let us take this pxy equals, now let us apply the limits, limit t tends to infinity, integral minus infinity to plus infinity. Then let us also apply the expectation here for this. So then expectation of x of f into y of f all divided by 2t into df. Then let us keep it and rewrite this equation by taking the limits inside. As limit t tends to infinity, then an expectation of x of f into y of f by 2t into df. Now comparing this equation with our the cross-spectral equation, so let us write the cross-spectral equation also. I'll call this as equation number 1. Let's save this page. So this is page. So if we take the cross-spectral equation in terms of time domain, then it is pxy is equal to an integral of minus infinity to plus infinity, that is sxy of f into df. Now from I call this as equation number 2. Now from equation 1 and 2, you can write sxy of f is equal to, we can write this as limit t tends to infinity, that is the expectation part. We can represent we can represent this as sxy of f, that is expectation of x conjugate of f and y of f by 2t. So this, we'll consider this as sxy of f. Then similarly in terms of yx, if I want to write, so yx of f is equal to, now what happens here is that as limit t tends to infinity, that is expectation, now this will become x of f into y conjugate of f by 2t. So that is the difference here, sxy of f and syx of f. So now if you apply our Fourier transform equation, or the relation of the autocorrelation and the cross-spectral relation equation for this, so then what will happen here is, or before going to that, let me rewrite this in terms of power. So then power for yx of f is equal to integral of minus infinity to plus infinity. Then syx of f into df. So by comparing these equation, that is equation 3 with equation 2, then we can write this as in terms of the power spectral density, that is sxy of f is equal to syx of f in terms of conjugate. It means it's a complex conjugate to each other. Now if we apply the exponential term to this equation 2 and 3, so that will become our the spectral, the cross spectral density. So let us write that. Let's save this page. I'll take the new page here. So then finally our spectral density equation will become sxy of omega, or this can also be written as j omega, which is equal to an integral of minus infinity to plus infinity, that is rxy of tau into e power minus j omega tau into d tau. So this we can obtain same way like how we have obtained the spectral density equations, by comparing the power equations of both the time domain and the frequency domain. So then the rxy of tau is equal to 1 by 2 pi into integral of minus infinity to plus infinity sxy of j omega into e power j omega tau into d tau. Now same way we can write for yx also. So therefore syx of omega is equal to integral of minus infinity to plus infinity, that is, now it is ryx of tau into e power minus j omega tau into d tau, and this is ryx of tau is equal to 1 by 2 pi into integral of minus infinity to plus infinity syx of tau into e power j omega tau into d omega. Sorry, here this term is supposed to be d omega. This is d omega. So this is about the cross spectral density. So next we are going to talk on the linear systems. So let me save this page. So thank you for watching this tutorial. So today we have discussed on the multiplication and the addition relation of autocorrelation and the power spectral density, and we have also seen the cross spectral densities. So thank you for watching this tutorial, and join with me in the next tutorial.